Any questions about anything? Well, I promised at the first day of class that by the end of class I would show you that Fourier series converge using things we've studied over the semester. And that's my plan for today. I'll be using a tool called the complex exponential, which people call the most important function in all of math. And you'll see why it's such an important thing in the context of Fourier series. In fact, it was invented for thinking about trigonometric functions, etc. Euler is famous for the Euler identity, which is that e to the iy is, let's see, so if I was going to do this, last time I came up with a power series for the exponential, that would be 1 plus iy plus iy squared over 2 factorial plus iy cubed over 3 factorial, etc. And let's see, you'd realize, oh, that's 1, iy is good, but I squared is minus 1, so that would be minus y squared over 2 factorial. And I cubed, let's see, I squared is minus 1, I cubed would be minus I. So this would be minus I y cubed over 3 factorial, plus etc. And when you pull that apart, you realize, aha, there's some stuff with I, and there's some stuff without I. You pull the stuff without I, and you get familiar power series for minus y to the 6 over 6 factorial. That's the familiar power series for the cosine of y. And then the I part here, let's see, the first I term is I times y, so that's y. Next one is minus y cubed over 3 factorial, etc. And this is the cosine of y, and this is the sine of y. So Euler, by doing that, sort of discovered the correct formula for the complex exponential and figured out all its basic properties. And I think E stands for Euler. Either that or exponential, who knows. So let's see. A fun thing to do, very much like what I did last time. If I write e to the e of x plus iy is the what it should be, e to the x cosine y plus I e to the x sine of y. It's kind of what it has to be. Then you can show that e is complex differentiable. So e prime of z, let's write e prime of z naught, is going to be the limit as the complex number z tends to z naught of the difference quotient, e of z minus e of z naught over z minus z naught. So not hard fact is to see that that limit exists, and when you actually mess around and calculate it, you see that the complex exponential is its own complex derivative. So this thing right here is called the complex derivative. And it's like doing freshman calculus all over again. And it's the subject matter of Math 425, which I'm also teaching this year. So this is number one. The complex exponential is its own derivative. And 2, an easy thing to check, is that e of 0 equals 1. And just like for the real exponential, these two things determine. There's only one thing that satisfies this, and it's the complex exponential. Okay. And then you can play all those same games that we did for the real one. So we would play the 8.3 games, and we find out a whole bunch of things exactly the same. We'd find out that E of Z1 plus Z2 is E of Z1 times E of Z2. And we would find that E to the minus Z is 1 over E to the Z. I guess the thing is E to the minus Z times E to the Z is 1. So E to the Z is never vanishing, and E to the minus Z, so E to the Z is non-vanishing. And E to the minus Z is 1 over E to the Z. It's complex numbers, etc. But when you do this one here, and do it for an E to the I, let's see, what would this one tell us? This would tell us that E to the X plus IY is E to the X times E to the IY. And then you can use Euler's observation and see that that's E to the X right. I mean, you can play games like that and see that that gives you the complex exponential that I wrote in the beginning. I won't write that. And let's see, you would also get that E to the Z is equal to a complex Taylor series that converges. And the radius of convergence, of course, is infinity. In the complex plane, and it's a true radius. It's a radius of a big circle. Anyway, those are facts, which I'll assume for the moment. Let's see. Here's the thing I need today, important. It's called de Moivre's formula. And it's E to the I theta to the nth power is equal to E to the I n theta, which is cosine n theta plus I sine n theta. Okay, that's an important thing. And the reason it's true is because E to the I theta times E to the I theta dot 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 n times is going to be E to the I theta plus etc. n times. This is n times. And of course, that's E to the I n theta. Check. So the basic facts imply famous formula. Okay, I'll come back to this in a minute, but this means, let's see, here's the famous formulas you learned in some place probably. Trig functions in terms of the complex exponential. Let's see, we have E to the I theta is cosine theta plus I sine theta. And E to the minus I theta would be cosine of minus theta, which is the same as cosine theta, plus I sine minus theta, which is cosine theta minus I sine theta. Okay. And you look at that for 10 minutes and realize, aha, if I add those together, the signs cancel. and I get that e to the I theta plus e to the minus I theta equals 2 cosine theta. So that's if I add them together. If I subtract them, then I would get e to the I theta minus e to the minus I theta equals 2I sine theta. And so the famous formulas you get here are that the cosine of theta is e to the I theta plus e to the minus I theta over 2. And sine theta is e to the I theta minus e to the minus I theta over 2I. Okay. All right, so I told you we're going to study Fourier series today. The Fourier series the big question is, we've got a function and we want to expand it as a Fourier series. So that's going to be the limit. We want f to be the limit as n goes to infinity of a partial sum of the Fourier series, where the Sn is going to be a naught plus the sum as n goes from 1 to capital N of an cosine n theta. Well, let's see, I'm going to switch to thetas. Well, I'll go back to x's. nx plus bn sine nx, where famous formulas are a naught is the average of the function, so that'd be a 1 over, we'll do on the interval from minus pi to pi. And the an's, the cosine terms, are 1 over pi, integral from minus pi to pi, f of x cosine nx. And the reason this formulas make sense is because of the orthogonality property that I mentioned on the first day of class. So Johann Bernoulli was able to figure out these formulas well before Fourier studied them. Okay, that's cool. But, oops, nx. Now, if I take that Fourier sum, so let's see. If I write out that Fourier series, that's a naught plus, the summation is n goes from 1 to capital N, an cosine is e to the I nx plus e to the minus I nx over 2. And let's see, plus bn, the sine function is e to the I nx minus e to the minus I nx over 2I. Okay, you pull that junk together, and you're going to get constant term. Let's see. Do this. Let's see. You get a constant term plus a sum as n goes. Let's see. I'm going to get some positive n's and some minus n's. So I'll get n goes, the positive ones will be something times e to the I nx. And let's see, what are those going to be? an over 2. Let's see, and then I'll get a bn over 2i. 1 over I is minus I. So that'd be minus I bn. And then I'll get some minus terms. Let's see, so the minus terms will be something times e to the minus inx. And let's see, the real part would be, let's see, I'd get an an over 2, and then I'd get a minus bn over 2i. But 1 over I is minus I, so I get plus I bn. And the cool thing is, you play around with this, and you realize, let's see, so what I'm going to write, let's write Cn equals an minus I bn over 2 when n is positive. And C minus n is going to be equal to an plus I bn over 2. Also, as n goes from 1 to n. Then I realized that that thing that looks like a real trigonometric polynomial, that's what those Fourier series are called, that's a sum from minus n to capital N of Cn e to the inx. Much simpler way to write the Fourier series. And when you play games and stick those formulas in, where the Cn are going to be equal to 1 over 2 pi integral from minus pi to pi of f of x times e to the minus inx dx. So the formulas become much simpler in the complex notation. They're 100% equivalent. Okay. That's an easy thing to check, that those CNs actually, let's see, I would check for positive n maybe. Check for n positive. Let's see, the Cn was an minus I bn over 2 from the calculation, and you write out what that is. That's the integral, that's 1 over pi, integral from minus pi to pi. The an is the integral of against cosine nx. Let's see, we have a half in front. I'll put the 2 in front. That's where the 2 pi comes from. And then I would have the minus I part. That would be minus I over 2 pi, integral from minus pi to pi of f of x sine nx. And sure enough, cosine minus I sine is e to the minus nx. So the last thing is to use that cosine nx minus I sine nx is e to the minus I nx. And similarly for the negative terms. Well, a wonderful thing about those, the complex notation, that's right. So now that I know this complex version of my Fourier series, the partial sum is a sum as n goes from minus n to n of Cn e to the inx. Okay, and the CNs now, I know, let's see, the CN is 1 over 2 pi, integral from minus pi to pi. I'll put the, I'll use the dummy variable here, f of t. This is, the Cn is the integral of f of t e to the minus inx dt. Okay, that's the Cn. And then I have here e to the inx. And I can move this e to the inx inside the integral. It's just a constant. The integral is with respect to t. So I can stick this in here. And then I get a formula, the summation, as n goes from minus n to n. 1 over 2 pi comes out in front. And then I would get let's see, I'll put the, this is a finite sum, so I can interchange the integral with the sum. And I get minus pi to pi integral, and then 1 over 2 pi, a sum as n goes from minus n to plus n. And let's see, this would be of e to the in x minus t, when I put that in there. And f of t I can pull out of that sum. And the dt, now I integrate. So I interchanged the sum with the integral. And got something kind of nice looking. In fact, oh my gosh, this is a geometric series. And so it's going to be summable. This is a famous thing called the Dirichlet kernel. And it's dn of x minus t. The famous Dirichlet kernel that Dirichlet was one of the teachers of Fourier. Okay, that's exciting. And in fact, the Dirichlet kernel is easy to analyze because it's just a geometric sum. So d of t, here's a mind-blowing thing. Mind-blowing thing. The Dirichlet kernel, dn of t, is something very simple. It's 1 over 2 pi sine n plus a half t over sine t over 2. That's a mind-blowing thing. And we can see it here because we know about geometric series. Here's why. dn of t is the sum, that's 1 over 2 pi. I'll take the sum of the minus terms, so that'd be the sum as n goes from minus 1 to n of e to the int, minus 1 to minus n. So that would be the minus terms. So that would be e to the int. Why don't I do this? There's the Dirichlet kernel. It's the sum of those exponentials with 1 over 2 pi in front. And so I'd have e to the minus int plus etc. plus e to the minus it plus 1 plus e to the it plus e to the it 2t plus e to the I nt. Okay, this one's cool. This I can pull out the e to the it, and then what I have left is 1 plus e to the it plus geometric series out to e to the I n minus 1t. This one I can do the same thing with, but this time I'll factor out an e to the minus int. And then I'd get 1 plus e to the minus it plus e to the minus I2t out to e to the minus I n minus 1t when I factor it out. Let me move that over a little bit. And the plus 1 in the middle. I'm not going to bore you to death with algebra, but that looks like a hairy sum to write out, but fascinating. This is a geometric series because of the de Moivre's formula. This is a geometric series, and it's equal to 1 minus e to the minus I nt, when I take n plus 1 there, over 1 minus e to the minus it. Because it's a geometric series. Because e to the I nt, or any t here. What? Okay, sorry. E to the I nt is e to the I t to the n. And so the algebra we messed around with, summing geometric series, goes over for complex numbers exactly the same. This one's 1 minus e to the I nt over 1 minus e to the it. And so I've got these simple expressions for that mess. And now I'm going to spare you the algebra. Algebra. It's not hard algebra. This mess is equal to, on the bottom, I get e to the it over 2 minus e to the minus it over 2 divided by 2I. And on the top, I get e to the I n plus a half t minus e to the minus I n plus a half t over 2I. And sure enough, those are the sign and the sign functions was expecting. So equals sine n plus a half. Oops, I dropped my 1 over 2 pi. Algebra, my 1 over 2 pi would hang along, and my 1 over 2 pi would hang along here. And I get the famous formula that Dirichlet determined. 1 half n plus a half t. Check. By the way, the value of that thing at t equals 0, you determine by L'Hopital's rule. So fascinating, L'Hopital's rule. The limit of that Dirichlet kernel as t tends to 0, the n plus first derivative would come out. Let's see, when I take the derivative of those things, I get n plus a half on top, and on the bottom I'd get a half. And that's, yeah, big. That's really big. what is it? It's 2n plus 1 over 2 pi. Big. That's why Fourier series are delicate. That's a great big thing. And if I were to graph the Dirichlet kernel, it's a beautiful thing to look at. Let's see, what does it look like? Minus pi to plus pi. It's this gigantic thing right here with a really concentrated area. And then it gets small. That looks pretty crummy. If only I could reflect. It's an even function, so that's messed up. It's getting closer. That's dn of t. Now let's see, easy things to check. An easy fact is that the integral of that thing is 1. Integral from minus pi to pi of the Dirichlet kernel is equal to 1. That's because of all those other, the term in the middle, the 1 term, is the one that integrates. All the others integrate to 0. Because integral from minus pi to pi of e to the int dt is a big fat 0 because they're trig functions that are 2 pi periodic, and they have area plus and minus that cancel. So you can just check that. Those are all 0 for n unequal to 0. Okay, that's an important fact. All right, let's see. Here's another. So here's the fact that I was going to show you. I can show it to you right now. Fact. If f is, let's say, C2 smooth is C2 smooth, so twice continuously differentiable, and 2 pi periodic, then the Fourier series converges to f uniformly. On the interval from minus pi to pi. So Fourier series really do converge. And here's how you see that. Here's a little lemma that's not hard to show. If f is 2 pi periodic, then it doesn't matter what interval you integrate f on. Let's see, what am I trying to say? The integral from minus pi to pi of f of t dt is the same as integral from a minus pi to a plus pi. It doesn't matter what interval you integrate on. It just has to be length 2 pi. Okay, the proof of that is easy. I'll give you a picture proof. So let's see. Let's see. I'll do it for something like sine and cosine. Here's sine. I'll do it for something weird. here's minus pi. I'll take one side be like this and the other side be like that. All right, it's 2 pi periodic, so the next one would be like that, etc. Okay, and let's say this is minus pi, this is plus pi, this is going to be plus 3 pi, etc. And if I integrate from, let's say right here, a, I'm sorry, here's what I meant to write here. A to a plus 2 pi, just an interval of length 2 pi. There's a. And I would ask myself if the integral from a to a plus 2 pi, that would be up here, okay, I'd have, so here's what it is, here's the proof. I would move this little bit of area up to here. And then I would have this little bit of area like that. And I would say, yeah, sure, I see it now. All I do is I shift that little piece of orange area over to the right and toss it in, and I get the same amount of area. Signed area, of course. So the orange stuff is equal to the orange stuff, and I just moved it. You can write a proof of that using change of variables formula and very formal, but that's the idea. So that's easy. Okay, so now I want to show you Fourier series converge. So the proof of convergence. Let's take Sn of x minus f of x. The Sn of x was the integral from minus pi to pi of the Dirichlet kernel of x minus t times f of t dt. And remember, the integral of the Dirichlet kernel, I'll make this be minus 1, minus f of x. Let's see. Now I'm going to do a change of variables. I'm going to let this x minus t be a tau. And then when I do that change of variables, this would become an integral from x minus pi to x plus pi. That's a interval of length 2 pi of dn of tau. T is equal to x minus tau, and dt is x minus tau. Yeah, this is going to be, when you do the change of variables, this is going to be a d tau. And I'll leave this as minus f of x. That's just the change of variables that you learned in freshman calculus. And I realized my lemma that's an interval of length 2 pi, so I can make that the integral from minus pi to pi of, these are all 2 pi periodic. And I'll change the tau back to a t. It's just a dummy variable. Okay, that's just a change of variables to I like the t being in the Dirichlet kernel. And now the big idea, one is equal to the integral from minus pi to pi of dn of t dt. And so this thing, I can make it look like that. I can write that as the integral from minus pi to pi of dn of t times this f of x dt, because that integral is 1. So that's a kind of a crazy way to write 1 times f of x. And f of x is a constant in that integral, so I could pull it out front. And so now I finally get something that's simple to write. My Fourier series minus my function is equal to the integral from minus pi to pi of the Dirichlet kernel of t times f of x minus t minus f of x. So all I've done is rewrite this in a form that's something we can analyze. And let's see. I know what that Dirichlet kernel is. That's the integral from minus pi to pi of 1 over 2 pi sine n plus a half over sine t over 2 times this thing. And I realized, aha, I know L'Hopital's rule. And so even though that sine t over 2 is 0 in the denominator, let's see, this would be equal to, I can pull a 1 over 2 pi out in front, integral from minus pi to pi, sine n plus a half t. And here, I've got this thing that looks like it might be bad. But when I stick in t equals 0 there, the top is 0 and the bottom is 0. Okay, so the exciting moment when you realize, oh my gosh, I'm going to see that Fourier series converge. L'Hopital shows this doesn't blow up. Shows the limit exists as t goes to 0, exists, and it's easy to calculate. Calculate. It'd be f prime over cosine, a half cosine 0. And in fact, you can use Taylor's theorem with remainder. So that's all I need is C1 for that to be the case. This is FC1 smooth. Would allow you to see that. FC2 smooth the thing inside the big square thing there would be C1 smooth. So not only is it continuous at the spot that looks bad, but it's differentiable there too. Okay? And in fact, you'd use a Taylor's theorem with remainder to see that in an easy way. The integral form of the remainder would be the way to analyze that. But now remember, you can integrate part by parts. I showed you that the Fourier series go to 0 by integration by parts. So finally, integrate by parts. And when you integrate by parts, let's see, I'd have the sine n plus a half over 2 t. That would be the dv, dt. That would be the dv part. And the thing in the square brackets would be the u part. U would be equal to the thing inside the square brackets. And when you do the integration by parts, a 1 over n plus 2 comes out. an n over 1 over n plus a half pops out. And that's how you show that the difference tends to 0. We see that the whole thing tends to 0. And in fact, it's uniformly in X. If you sit down and think about the error, see the whole thing goes to 0 uniformly in excuse me, X. Okay. Interesting, if F was only C1 smooth, we could still get we could still get convergence. But, yeah, I don't want to go overboard today. But C2 smooth, it pops out very easily. We know everything you need to know, we know in this class to do it. Okay, so this class today has been an advertisement for understanding the complex exponential. That's 425. That's where you learn about e to the z and power series with complex numbers. And Math 428 is where you study Fourier series more deeply. So those are sort of senior capstone math major classes. And at this moment, you're ready for both of them. That's what I wanted to convince you of. Any questions about Fourier series? It's really beautiful stuff, and even though it maybe looked a little hairy and computational, all those calculations I did are pretty routine. You just have to sit down and do them. And the amazing thing is that when you sit down and do them, the formulas collapse into something manageable that we can study with the tools we've learned in Math 341. Okay, I have now fulfilled my promise. Anyway, I'll defer on Wednesday and Friday. I'll do a review. Wednesday, Friday. Review. So if you want to get ready for review, think about questions about homework problems you might have, or I also gave you some review problems to look at, which I think are nice. They come from exams at MIT, but that's the type of there's so many of them that they can't be too hard. A couple of them might be tricky, but I think they're routine knowledge kind of questions. So that course at MIT, which is parallel to this course, seems quite reasonable. It's just a lot for one exam. I would never give that many questions. It's too much. But I don't think the level of difficulty is too hard. There's just too many of them. A couple of them are tricky, but if you have questions about those, bring it up on Wednesday or Friday. Let's see, when the exam is mentioned on the home page, I believe. Is it the Friday? Yeah, it's the Friday one. Anyway, I'll say more about that later. Okay.
On page 4, I think.
4?
You pulled out the e to the it and e to the negative it.
Yeah.
I think one of those has an extra n.
That's very possible. I'll fix that when I post it. Way back here.
Yeah, let me think.
E to the I.